Okay. Assalamualaikum. So we started talking about multiple regression model. And in the last class, we said that multiple regression gives us a way to measure causal relations. Um, so, and that's one of the ways in which we can measure whether X causes a change in Y and how large is the effect of X on Y. But that's not the best way of trying to measure it. It gets us some way along that path. But the critical assumption that we need for us to be sure that what we are measuring is the effect of X alone and not some other variable having an effect on Y at the same time is if we can justify making an assumption, the zero conditional mean assumption about our regression model. What is the zero conditional mean assumption? Anyone? The mean independence assumption. What is it saying?
It says that the error term is computed to all the variables present in the regression.
The error term is what of all the variables? Sorry, could you middle part? The error term. Go ahead.
Sorry, sir, my internet's a bit unstable. Could you please repeat?
No, I was just saying that you said the zero conditional mean assumption is saying something about the error term and the X variables in your model. We missed, at least I missed the middle part that you said. What specifically does it say about the error and the variables?
So it's basically that the average of error term is independent of the other X variable regression.
Yes, exactly. So the mean independence assumption is that the error term in your model, what is the error term in my model? Can we unpack that variable U? What is it in reality? It is basically everything that affects Y that I have not included in my X variable set, right? So the error term, which is everything that affects Y but is not in my model, should be mean independent, uncorrelated. That's a weaker form of saying that, but really it should be mean independent of the variables that I do include in my model. That's the zero conditional mean assumption. So in order to be sure that our beta 1 coefficient, the slope coefficient, is measuring the causal effect of X on Y, that assumption, we should be justified in making that assumption. That assumption should be true about our regression. Now, obviously, it's really hard to evaluate whether or not that assumption is true about any given regression model. I mean, all we can do, so there's no direct statistical test of that assumption. For the reason that we don't have data on the error term, that's one reason. But the other thing is that the residual, the OLS residual U hat, that we can use to calculate the variance, even though हमें error variance sigma square के लिए भी तो U पे data चाहिए, which we don't have, but we use the OLS residuals in place of U. It works fine for that calculation, but we cannot, especially for testing this assumption, because the residual is really a good proxy if this assumption holds. We'll talk about that later in this course. So there's no direct way of checking whether or not this assumption is a valid assumption about our regression model. And it is, as you can see, a really strong assumption because it is saying something. It is a statement about the error term, which really could be literally hundreds of different variables in it, right? It's a composite variable. It is not a single one variable. It is many different variables, all of whom affect Y, are correlated with Y. So we are saying that none of those variables that we have omitted from our regression model should have any relation on average with the variables that we do include in our model, the X variables, the explanatory variables. So because there's no direct statistical test whether or not this assumption is true for a given regression model, all we can do is we can think about what the error term contains. Are there any potential confounding variables in it that we need to collect data on and control, add as a control in our regression? That's the multiple regression approach, right? You think about the error term and everything it contains. You think about, okay, which variables in that list are not likely to be correlated with X, so I don't need to worry about them. Which variables are correlated with X, and I do need to collect data and control for them. But if I do that, the problem with that approach is that we don't know where to stop adding more controls, because the assumption that we need to satisfy at the end of the day is still a very strong assumption. And people can come up, our critics can come up with other omitted confounding variables that we have not controlled for or collected data on. There may be variables that we cannot collect data on because we don't know how to measure them very well, right? There may be some unmeasurable traits, preferences of individuals that there's no universal agreement on how to measure those things. So, multiple regression is a really good tool. It is definitely better than a simple regression. Simple regression mein to you are guaranteed that beta 1 coefficient is not the causal effect. You're almost certain, except one situation that I'll talk about just now. But multiple regression mein ye hai ki at least you will be able to say, okay, I have controlled for these other 4 variables, 3 variables in my model, and keeping their values fixed. If I were to increase x1 by 1 unit, the associated change in y will be beta 1 hat, right? So this gives you a kind of a partial correlation. Keeping these 3 variables fixed, what is the correlation between y and x1? You may not be able to claim that this is the causal effect of x1 on y, because that requires really convincing people that that assumption, zero conditional mean assumption, is true. But that's still better than a simple regression. So what was the second approach? The second approach was that instead of listing down what is in the error term and trying to control for confounding variables in that list, you essentially, instead of just collecting data, if you could actually intervene and change the value of X yourself for some individuals, not for others, right? If you could run an experiment, a randomized experiment, where the value of X was not chosen by your study subjects themselves, it was specified by the research. So some people were randomly put in a treatment group. They got a higher level of X. Some people were randomly put in the control group. They got a lower value of X. And then at the end of the experiment, we compared the average Y value in the treatment group with the average Y in the control group, right? So that's how an experiment would run. And the word randomly is important, right? So even when I'm running an experiment, I could do it in a poor way, right? I could try and use my own judgment to decide कि किसको college education देनी है, किसको नहीं देनी, right? And that will still not be a good way to measure the effect of college education on wage, because my own decision could introduce biases, right? And it's not replicable. So when you are changing the value of X, it's important to do that randomly, randomize people into treatment and control group. And once you do that, you are guaranteed that all other confounding variables will be balanced across the 2 groups. So ऐसा नहीं होगा कि जो लोग college education ले रहे हैं, they tend to be higher ability individuals with wealthier parents who are really motivated about education, right? Because individuals are not choosing whether to get college education or not. It's you as an experimenter who's tossing a coin and deciding which person gets college education, which person does not, right? So if you could run such an experiment, it's not ethically, you will not be allowed to do that research study. So all research studies need a certain minimum ethics approval. But imagine for now, just for the sake of the argument, that we could run that experiment, then the decision to go to college is not made by an individual based on their own preferences, costs, and benefits. It has been made by that outcome of the coin toss. And the outcome of that coin toss, which determines the value of X, whether someone gets college education or not, is what? Can we say that the zero conditional mean assumption holds? If the coin toss determines college education?
Yes, sir, because then they are independent variables.
Yes. So the outcome of the coin toss is independent of everything about each individual, right? To think of it differently, we created two random groups, treatment and control. Some people are being put into the treatment group, some people are going into the control group, because we are tossing a coin to decide who goes into treatment and who goes into control. कुछ treatment group में कुछ high ability लोग भी होंगे जिनके लिए the coin landed heads and they were asked to go to college, but some low ability people will also be there, because the coin landed heads for them, they were not choosing themselves. So the average ability in the treatment group will be the same as the average ability in the control group. So this particular confounding variable, which we were worried is going to be correlated with college education in a non-experimental study, because we are running an experiment, our treatment and control group have the same level of average ability. They have the same level of parental wealth, same level of parental aspirations about their education and everything else. So all other variables that could be in the error term U are going to be on average the same in the treatment group as the control group. So the average value of ability in treatment equals the average value of ability in the control, just because we are tossing a coin to put people here or there, right? So आपके जो treatment और control group बनेंगे, उनकी average ability, वो दोनों groups बड़े similar होंगे on all other traits, except that one groups get college education, the other does not, right? So that's the method of randomized experiments. And if you can do an experiment like that, then a simple regression is fine, because the zero conditional mean assumption will be satisfied. The beta one in that regression will give you the causal effect of college education of your X variable on Y. But in all other situations where we don't have an experiment to rely on, where we are collecting data, it's not an experiment. In a non-experimental setting, we are just doing a survey and wanting to analyze that data to estimate relations. It is really hard to claim, unless you can justify making the zero conditional mean assumption. It is really hard to justify that what you are measuring is the causal relation. Okay, but so having said that, let's come back to the multiple regression now and try to understand, or at least compare it with the simple regression. कि वो जो multiple regression में beta 1 coefficient है, उसका formula क्या है? How does it compare with the OLS estimator formula that we've seen before in chapter 2 for the simple regression? वो formula अगर different है, तो what does it mean? Can we make sense of the difference in the two formulas? It will be different, obviously. But you know, so multiple regression में और भी X variables आ गए हैं right hand side पे. So maybe their values also have an effect on beta 1 hat की क्या value है slope की, right? It should have some effect, one would expect. So we want to talk a bit about that, कि हमारे जो OLS estimates हैं in a multiple regression versus the OLS estimates of the same coefficient, the beta 1 coefficient on the first X variable. How do they compare? We want to look at the variance formula really quickly, because variance, abhi tak to we haven't really used the standard errors. In fact, if you look at chapter 2, the examples in that chapter, and even chapter 3, they don't start talking about really about the standard errors. So we derive the formula for the variance of beta 1 hat, but we haven't really started using it. So we can look at that formula, see what difference does adding more x variables to the model make to the standard error of our estimates, if at all, if any difference is made there, and so on. So we want to just quickly go through some of the key ideas in chapter 3 in today's lecture, and then end on this note of, okay, how do we start uh, generalizing to the population relation based on our sample analysis. So how do we do statistical inference, which is really the topic of chapter 4. So the goal, the ambitious goal, is that we fill. So I will go relatively quickly through chapter 3, because it is really an extension of chapter 2. So if you have understood chapter 2 really well, you studied it for the quiz and have understood what we are talking about there. Chapter 3 is just adding a few more x variables to that regression model, and then talking about, okay, what happens now if we estimate this model using OLS. So it's a fairly simple extension of what we have learned already. We'll talk about, okay, under what assumptions. So what is the expected value of beta 1 hat? What is the variance of beta 1 hat? What properties does the OLS estimator have under different assumptions about the model, and so on. So I'm not going to go into all of those details. We will point you to recorded lectures from last time if you need more detail. Obviously, there's the textbook, so you can read. You should definitely read chapter 3 and try to make sense of that. So, any questions before I start a deeper dive into? Any questions about the causal effect estimation? Because we are not going to talk about that again for now. So that issue we've parked. The main takeaway message was that if you can run a randomized experiment, do that. That's the best way to satisfy the zero conditional mean assumption. If you can't do it, then there are other methods available. Multiple regression is one of them. So we are just going to stop that discussion now and try to understand multiple regression. But if there are any questions. Okay. So we have already seen the equation of the simple regression. The equation of linear multiple regression just has some extra variables on the right hand side of the equation. The x1, so obviously since I have more than one x variables, I need to number them. So x1 is the first x variable. It's the same as the x variable there. In fact, let me call this x1 just so that everyone is clear that x1 is the same variable that we had in this model. Now, in addition to x1, I have a bunch of other x variables in my model as well. Now, this is the general form of writing a linear multiple regression. A multiple regression that is linear in its beta coefficients. So each beta coefficient comes separately with a x variable term, right? With an x variable attached in this model. In the case of beta 0, obviously there's no x variable. You can think of x variable as x is equal to 1. So there's a variable x0 in my data set, which takes the value 1 for all observations. In that case, beta 0 is also multiplied by x, because beta 0 is just a constant. Beta 0 multiplied by 1 is beta 0. And so I have this multiple regression. Now I want to, so the first problem is estimating the coefficient. So these are population regression models. They have some unknown beta parameters whose values we would like to know using data. We would like to estimate those values. So we know how we do that in the case of a simple regression. We can use the same method, minimize the sum of squared residuals, the ordinary least squares method, to obtain estimates of the beta coefficients in a multiple regression. Now, the only difference would be that your objective function, you will be minimizing that function with respect to not 2 parameters, but with respect to all of these beta parameter values, k plus 1 parameters. So you will differentiate that objective function with respect to each coefficient, put that equal to 0. So you will get k plus 1 equations in k plus 1 unknowns. You can solve that system of equations simultaneously and obtain the formulas, the OLS formulas for each of these estimators. So we've done that exercise for the simple regression. We don't need to do that exercise because you need matrix algebra for that. We don't need to go through the math of that. We can just look at the end product of when you do that, when you solve that system of linear equations, what do you get? So let me give you, let me write down the formula on this side first, because we are familiar with it. And then I'll come back to, and I'm to this side, and I'm going to just focus on the slope coefficient. Let's ignore the intercept for now. We are just going to focus on the slope coefficient formula. So the OLS estimator for beta 1 hat equals what? Can someone give us the formula? Someone who remembers it? Simple regression में कैसे estimate करते हैं? So what's the formula that we use?
So it's summation yi minus y bar multiplied by xi minus x bar over summation xi minus x bar.
Right. So exactly, and you can also think of that as the new. So it's a ratio. Numerator में आपके पास sample covariance है between y and x, और denominator में sample variance है of the x variable. But we do need that summation, the detailed expression that we just mentioned. So summation, and I'm going to, instead of using that full form yi minus y bar times xi minus x bar, I can drop one of the two sample means in that formula, right, without changing it. So let me write down this version, xi minus x bar times yi. So I'm not putting the yi minus y bar, I dropped the y bar, divided by xi minus x bar whole square, right? So this is also xi minus x bar times xi minus x bar. So I could have written as a dropped the second x bar and written it as xi minus x bar times xi, right? So that you should all be familiar with. That's a simple trick. We can do that. So if we have a product of two demeaned variables which are each of those variables is subtracting its mean from it. So in that product, nothing changes if I drop one of the two sample means. I can't drop both, but I can drop either y bar or x bar from that product. Nothing changes. Okay, so this is how we can write the OLS slope estimator in this model. Over here, if I wanted to know the OLS estimator formula for beta 1 hat, let's call it beta 1 tilde just to actually let me call this tilde and this hat just to distinguish because there are we will see that there are different formulas for it. Okay, so what's the formula OLS formula for this? So it turns out that that formula is obviously way too complicated. If I want to write it in the form of my original variables, y and x variables, it's not going to be a function of y and x1 alone, right? Sorry, I said I'm going to do this one. So this in the multiple regression, even though हम x1 के slope coefficient को estimate करने की बात कर रहे हैं, but that estimate is not simply going to be a function of y and x1. In fact, it's going to be a function of all the x variables in general, right? Because you can imagine that I have k plus 1 equations and k plus 1 unknown. So जब मैं उसको solve करूंगा तो कोई complicated सा formula ही आएगा, right? जिसमें सारे variables आ रहे होंगे. So पहली बात तो ये है कि in the form of my original variables in the model, this formula is some complicated formula of all the variables, the y and the x variables in my model, right? Not just y and x1, दूसरे x variables भी हैं. So that formula is not present. Sorry, it's not pretty to look at. It's a really complicated formula, and it's better to express it in the matrix notation. So I'm just going to write down the matrix formula. You can totally ignore it. That's a graduate econometrics class. We haven't derived it or anything. But आपने OLS estimator अगर estimate करना है तो you do this. So you have a matrix capital X which has all the x variables in it. Each x variable going down a column, all the observations. So x transpose x, that's a matrix. Invert it and multiply it with x transpose y, where y is your vector of n observations on the y variable, right? So this is a vector, this is a matrix. The result is going to be a vector of beta coefficients. So obviously there's no simple way of expressing it. Pulling out one beta coefficient from that formula, but you can see that that formula tells you that this beta coefficient, beta 1 hat, is going to be a function of all the beta. There is though a simpler form of beta 1 hat, which is quite intuitive and actually you learn more by looking at that formula. That's the one that we talk about in chapter 3 of the book. So let me give you that formula. So that formula is not in terms of these x variables. So what is the formula? So it says again it's a ratio. In the numerator you have r1 hat I times yi. In the denominator you have r1 hat I squared. Now, what is this R1 hat? राइट, बिकॉज अभी तक तो हमने कोई आर हैट नहीं देखा इस मॉडल में. So this R1 hat is really interesting. It's a new variable and it's in fact a residual from a regression. So this R hat I, let me define it over here, is a residual from a regression of x1 on all the other x variables. If I regress x1 on x2, x3, all the way up to xk, all the variables in my model, other variables. So मैं x1 को इन सारे variables पे अगर regress करूं, that's a regression, right? I could run that. I have data on all my variables. I could run that regression and obtain a residual from that regression. So I could estimate that regression using OLS, and then there will be some fitted values, x1 hat from that model. So essentially, I'm saying, okay, let's run a regression x1 alpha equals alpha 0 plus alpha, or rather, we call it alpha 1 plus alpha 2 x2 plus alpha 3 x3 plus alpha k xk plus some error term epsilon. And if I could estimate this regression. I have data on all the variables. I could estimate the alpha coefficients using OLS. And once I do that, I can write x1 as a fitted value plus a residual. And that residual is what we are calling R1 hat. Right? Okay? Is that clear? कि ये R1 hat कहाँ से आ रहा?
So why are we running a regression on x's and not our main purpose is to do a regression of y on the x variables, right?
Yeah, that is the main purpose. Our main purpose is to estimate this beta 1 coefficient, which tells us what is the relation between x1 and y. And in estimating that beta 1 coefficient, we came across this thing, this new object R1 hat. And we are saying, what is this R1 hat? Because there's no R1 hat in our model. So I'm telling you that this R1 hat is actually, if you were to run a regression of the x1 variable on all the other x variables and obtained the residual from that regression, that's R1. So we don't
So
make,
ये
you're
नीचे
right.
I क्यों नहीं आती? Why do we use the I in the subscript?
Oh, that's just because we have I stands for an observation in our sample, right? So we have n observations. So I goes from 1 to n. So yeah, so this I now becomes, I think पहले आपको confuse नहीं कर रहा था, आप confuse इसलिए करने लग गए because x के नीचे एक वो counter भी लग गया ना, multiple x variables. So we say that we have, so the general form of the explanatory variable has now become, it has got two subscripts. So xji, where j indicates the number of x variables in my model, right? So the index j goes from 1 to what value? It goes up to k, right? Right, so k is bigger than 1. This is a multiple regression I'm talking about. So एक से ज़्यादा x variables है मेरे model में. So k has to be, this k better be greater than 1. Because if k equals 1, then we are back in the simple regression. So k may be some value like 5, right? So my indicator j goes from 1 to 5 in that case. And I have this other subscript जो पहले भी था हमारे पास, which was indicating the number of observations in my sample. The number of individuals on whom we collected data, right? And I की value, I क्या values लेता है? What values does I take? This index, second index.
So जितनी भी observation होंगी.
हाँ, तो 1, 2, 3 up to what?
N.
जी. So sample size को हम n से denote करते हैं, right? So I goes from 1 to all the way up to n, where n is the sample size, the total number of observations in my sample, right? And k is the number of variables, explanatory variables in my model, in my regression. ठीक है जी? So आपके जो x variables हैं multiple regression में, they now have these two indicators, j and I. I तो is the same old I, which stands for different observations. So when we are summing anything, we are summing over I, right? So that's why we put an I subscript. I की different values आप put in करेंगे. So this sum essentially has these product terms in it. So the first term in the sum will be R1 hat times Y1, R11 hat times Y1 plus R12 hat times Y2 plus R13 hat times Y3. So basically वो different observations के लिए आपको residual की value देगा, R1 hat की value. और R1 hat क्या चीज है? वो है residual when you regress X1 on all the other variables. And so basically वो residual के नीचे जो हमने 1 लिखा हुआ है, that is coming because our dependent variable is X1. अगर हम beta 2 hat की बात कर रहे होते तो यहाँ पे R2 hat होना था, because we would have regressed X2 on all the other X variables and obtained the residual. उस residual को हम R2 hat कहते हैं. So this one comes with the one under the beta hat. तो क्योंकि हम beta 1 hat की बात करें इसलिए यहाँ पे R1 hat है. अगर beta 2 hat की बात करेंगे तो यहाँ पे R2 hat आएगा, right, and so on. Okay. बल्कि in fact अब हमने इतनी बात कर ही ली है तो let's make this formula more general. Let's call it beta hat J. Or in fact, let's not, because I want to compare the two beta 1 hat formulas. So let's keep the one for now. Okay.
Sorry, to alpha 1, alpha 2 है ये is this telling us the beta 1, beta 2 की substitutes हैं?
No. So these alphas have no relation to these betas. That's why I'm using a different symbol for it. This regression, going back to an earlier question or comment, we are not interested in this regression at all. So this is like an extra additional regression that we are running. All we are interested in is in estimating this original regression. So इस regression को आप एक extra या auxiliary regression कह सकते हैं. So this is a regression that is an accessory. It helps us in estimating the coefficients in this model, but by itself we are not interested in these alpha parameters, right? Because we are not interested in कि वो x variables आपस में किस तरह related हैं, उनकी क्या correlation. If we were interested in that, obviously we would be interested in this regression, but we are interested in how y is related with these variables, with x1 in particular. ठीक है जी? Okay. Now let's look at these two formulas. Let's try to compare these two formulas. This is a ratio of two sums. This also is a ratio of two sums. इसमें numerator में y आ रहा है, इसमें भी numerator में y multiplied with something else आ रहा है. इसमें डिनोमिनेटर में जो सम है वो स्क्वायर्ड चीज का हो रहा है, राइट? इट्स अ सम ऑफ स्क्वायर्स. यहाँ पे भी डिनोमिनेटर में इट्स अ सम ऑफ स्क्वायर्स. सो सिमिलैरिटीज तो हैं काफी, राइट, दोनों फॉर्मूलाज. बट देयर आर आल्सो डिफरेंसेस, राइट? फॉर एग्जांपल यहाँ पे जो चीज है वो x1 है, यहाँ पे देयर सम न्यू थिंग वी आर कॉलिंग r1, राइट? r1 hat उसकी एस्टिमेटेड चीज है, राइट? This was our original variable in the data. This is something we are estimating using our sample data. We are estimating this regression और उसके residual को फिर हम use कर रहे हैं in this formula. But ignoring that for now, कि यहाँ पे x1 है और यहाँ पे r1 hat आ गया, वो r1 hat भी तो x1 में से निकल रहा है ना, उसका leftover part है, residual है. What's the other difference in the two formulas? Can you spot some other difference? So similarities तो मैंने आपको काफी बता दी हैं, एक difference भी बता दिया. Is there any other difference? बोलो भाई. अगर हमने दोनों फॉर्मूलाज में सिर्फ एक ही डिफरेंस होता कि x1 is replaced by r1 या r1 hat, अगर हमने इस फॉर्मूला का एक वर्जन लिखना होता है in which we simply replace जहाँ जहाँ x1 आ रहा है उसको r1 hat से रिप्लेस कर दें, तो हमारे पास ये फॉर्मूला आना था या कुछ और फर्क चीज आनी?
सर एक रेजिडुअल ऑफ रिग्रेशन है और एक वेरिएंस है जैसे डिनोमिनेटर में.
नहीं वो तो है. आई एम सेइंग कि लुक एट दिस फॉर्मूला. If I were to replace x1 in this formula, जहां जहां x1 आ रहा है उसको मैं r1 hat से replace कर दूं अगर, तो would I get the same thing as I have over here or would I get something else? So take this formula, replace it with x1 with r1 hat. जी sorry, go ahead.
सर वो क्योंकि मीन से सब्ट्रैक्ट हो रहा है.
जी exactly. So ये वाली जो चीज है, जो मीन सब्ट्रैक्ट हो रहा है वो यहाँ पे नहीं हो रहा, right? There is no subtraction of the mean happening. So अगर इसका direct counterpart analogous formula आप सोचें which simply replaces x1 with r1 hat, so the formula that you would get would be in the numerator r1 hat I minus its mean, r1 hat का mean times yi, and in the denominator you would have summation r1 hat minus its mean r1 hat bar squared. So ये जो माइनस हमने करना था r1 hat bar को, बस वो काम नहीं हो रहा इस फॉर्मूला में, बाकी सारा कुछ तो वही. But because this is an OLS residual, we know a property of OLS residuals. What is that property? This is a residual from this regression. So whenever you estimate a regression using OLS and obtain its residuals, those residuals have certain properties. We talked about that in chapter 2. What are some of the properties of the OLS residuals?
Sir, some
What's
of
the
the
number?
residuals would be 0.
Yes. So the number one property of an OLS residual is that it sums up to 0. उसका मीन जो है रेजिजुअल का वो 0 होता है. सो ये मीन वैसे ही 0 के बराबर है, बिकॉज दिस वेरिएबल इज अ रेजिजुअल फ्रॉम अ रिग्रेशन, उसके मीन 0 के बराबर है. सो essentially this formula and this formula are no different. ये वाला फॉर्मूला जो है वो यही फॉर्मूला है, उसमें x1 को हमने रिप्लेस कर दिया with r1 hat, and knowing that r1 hat is a residual with a mean of 0, if we simplify we get this form. ठीक है जी. So how significant is that? What do we learn from it? Why is it important that the multiple regression beta 1 formula, OLS estimator का formula, is similar to, analogous to simple regression का beta 1 form? So it is analogous but not exactly the same. So it's important. So there is a difference in these formulas, but there are also parallels. What do we learn from this discussion? All of you must be thinking like, I learned nothing. I'm confused. Okay. All right. So so this formula over here is how we calculate beta 1 in a multiple regression. This formula over here is how I calculate beta 1 in a simple regression where I don't have any other x variable in my model. That's how I compute beta 1. When I have other x variables in my model, this is how I compute beta 1, right? Now, effectively, that allows us to link the multiple regression. This connection between the two formulas allows us to link this multiple regression and the simple regression. So the multiple regression can be thought of as a two-step regression procedure, where in the first step, the multiple regression coefficient beta 1 can be obtained as a two-step procedure. In the first step, you run this auxiliary extra regression, which we are not, जिसके alpha coefficients में हमारा कोई interest नहीं है. So we run this regression and obtain R1 hat. We are interested in the residual from this regression. So we obtain those residuals. Then what do we do in the second step? So the second step is effectively, if we want to get this formula, we can get this formula by simply regressing y on R1 hat, running a simple regression of y on this residual R1 hat. Right? Okay. So the second step is a simple regression. I've written it underneath the column of simple regression. So when I regress y on R1 hat, I only have one variable in my model, the residual R1 hat. उस मॉडल का जो beta 1 कोफिशिएंट होगा, जो स्लोप कोफिशिएंट होगा, forget beta 1. So इस मॉडल में जो स्लोप कोफिशिएंट है, उसका OLS estimate will, obviously I will apply this formula, keeping in mind that my x1 variable is now R1 hat. So I'll replace x1 with R1 hat everywhere. And also keeping in mind that this R1 hat is a residual, so iska mean 0 hoga. So I plug the value of 0 here, and what do I get? I get exactly the same value of, so the slope coefficient here after step 2, the slope coefficient that I get will be equal to which slope coefficient? So let's say I regressed y on r1 hat. Let's call those coefficients deltas, delta 0 plus delta 1 r1 hat plus an error term. So that's my second stage regression. So in the first stage, I regressed x1 on all the other x variables, obtained r1 hat. In the second stage, I regressed y, my original dependent variable, on r1 hat. And so the slope coefficient in this regression, the OLS estimate of it using this formula, but applying it to r1 hat instead of x1, I will get an estimate for delta 1 hat, right? That estimate will be equal to which estimate of beta 1? The simple regression estimate of beta 1 or the multiple regression?
There's a simple one.
अरे नहीं भाई, simple one कैसे? So this delta 1 hat will be equal to beta 1 tilde or beta 1 hat?
Beta 1 hat, sir.
G. Thank you. Right. So if I was interested in obtaining a coefficient, the slope coefficient on x1 controlling other x variables, I could run a multiple regression. That would be the most natural thing to do and use this formula. So when you ask Stata to run a multiple regression, regress y, x1, x2, x3, yeah, regress wage, education, experience, tenure, right? That's the Stata command you give. Stata calculates the coefficients in that model using this formula, right? And Stata does not need to do this two-step procedure because, as I said, there's another expression for this formula, which is in terms of the original variables. I wrote the matrix equivalent of this formula and erased it, right? So Stata can use this formula to directly tell you the values of these beta coefficients in your multiple regression. Alternatively, you can do, if you were only interested in one slope coefficient in this model, the beta 1 in the multiple regression, you could do a two-stage regression, two-step regression, where in the first step, you regressed the associated variable x1. आपका beta 1 में अगर interest है तो आप x1 को regress करेंगे बाकी सारे x variables पे obtain the residual. We call that residual r1 hat. In the second stage, you run a simple regression of y on r1 hat. So वो जो second stage regression का slope coefficient है वो वही होगा जो आपका multiple. So effectively, you can obtain the multiple regression estimate of beta 1 using this two-stage procedure instead. So what does that tell us? Why is that useful to know? What does it tell us about the multiple regression? So it gives us a way to think about the multiple regression. What effectively adding these other x variables is doing to my beta 1 coefficient. So if you think about this two-stage procedure, what it does is, first of all, it regresses x1 on these new x variables and removes their effect from x1. So there is a part of x1 that is explained by other explanatory variables, right? There's a part of x1 that is correlated with the other variables, and there's a part of x1 that is not correlated with the other x variables. So think of this residual as the leftover part of x1 after I take away the influence of these variables on x1, right? So just to go back to a concrete example, हमारा x1 variable था whether someone graduated from LUMS or not, whether someone has a LUMS degree. That was our x1 variable. Our x2 variable, the confounding variable we were worried about was a, higher ability students might be going to LUMS. There might be a higher chance of them going to LUMS. So x2 is a IQ score or SAT score, some measure of ability. x3 might be parents' income, right? So elite parents, parents who can afford LUMS education, send their kids to LUMS, right? So and so on. So X2, X3 are ability, parents' income, and these are the variables. Those variables are correlated with X1 variable, right? So let's net out the effect of these variables on X1 and come up with, so think of this residual as X1 net of its correlation with the other X variables. Right? So X1 की जो भी correlation थी इन दूसरे variables के साथ वो मैंने अब remove कर दी. When I'm looking at the R1 hat, it is the leftover variation in X1. After I take away that part of X1 which was correlated with all these other variables. And then in the second stage, I'm regressing Y on that netted out portion of X1. So X1 was whether you have a LUMS degree or not. We thought that that could be correlated with some other variables. So we put those correlated variables in our regression. The effect of adding those controls is कि वो जो beta 1 coefficient है X1 का, this is now measuring the correlation between Y and X1 minus the correlation that X1 has with these variables, right? So after so think of that as X1 purified of its correlation. So this is a part of X1 that's uncorrelated with ability, with parents' income, etc., etc. So this beta 1 is, will the two estimates be the same? No. So in general, beta 1 hat is not equal to beta 1 delta, right? So the estimate that you will get on your slope coefficient from a multiple regression will not be the same because they are coming from two different formulas, right? So as long as X1 has some correlation with the added variables, and if those added variables have non-zero coefficients, these two coefficients will not be. So in general, I can say that there will be some situations in which adding more variables has no effect on the existing slope coefficient. But in general, the two estimates will be different. One estimate is really looking at the effect of X1 after removing the correlation, X1 net of these other variables, removing the correlation of other variables from X1. How does it affect Y? How does it correlate with Y? The other one is measuring the overall change in Y and assigning all of that to the change in X1. So it's giving you the total, the direct as well as the indirect effect of X1 on Y. Okay, I have to stop and we need to take a quiz, attendance quiz. But if there are any quick, short questions about this, you can ask.
Sir, ये आप repeat कर देंगे इन दोनों में difference? It was a bit confusing.
नहीं repeat नहीं हो सकता. मैंने इतने 10 मिनट लगा के बात की. कैसे repeat करूं? What is it that you are confused about?
सर आपने ये जो tilde वाला कहा है उसका कहा है कि it gives both direct and indirect effect of X on Y, है ना?
जी.
और जो आपने beta 1 hat के कहा है, आपने कहा है कि it isolates the effect of the residuals from the values of X.
No, it
Is that right?
So basic, yeah. So okay, let me try and make a diagram here. So this is the Y variable. This is X1. X1 has some effect on Y, direct effect. Let's call it beta 1 hat. But X1 is not the only variable that affects Y. There are other variables, X2, X3, up to Xk, and then there's the error term 2 as well, right? So all of these variables have some effect on Y, right? So अब ये वेरिएबल्स मैंने अपने मॉडल में ऐड कर दिए हैं. इन अ सिंपल रिग्रेशन ये एडेड नहीं थे, राइट? तो क्या हो रहा था कि ये वेरिएबल्स x1 के साथ भी कोरिलेटेड हैं, राइट? So they have some correlation with x1 as well. So in a simple regression, what was happening, because I did not have these variables added in my equation, I was simply measuring the change in y associated with the change in x1, where these other things could have also changed. So the total, so I was actually, the estimate beta 1 tilde was not only giving me just the direct effect of x1 on y, holding these other things constant, netting their effect out. It was actually measuring the total change in y and the change in x1 and saying that all of that change in y must have happened due to x1. So beta 1 tilde was actually, so let me simplify this slightly. Let's say that in variables में से सिर्फ x2 correlated x1 से. So पहले क्या हो रहा था, beta 1 tilde, beta 1 hat direct effect भी दे रहा था और ये indirect effect जो हो रहा है through x2, because as x1 increases, x2 is correlated with x1. Let's say that also goes up, right? इसकी value बढ़ती है, इसकी value भी बढ़ जाती है because the two are correlated. और इसकी value बढ़ने से y पे effect आता है, x1 की value बढ़ने से एक effect आता है और एक additional effect आता है x2 की वजह से, right? So which is this indirect effect arising because x2 has an effect on y, right? And x1 has an effect on x2. So this is an indirect path through which x1 affects y. This is the direct path. So beta 1 tilde is the sum of this direct effect plus the indirect effect. So that's why we didn't trust beta 1 tilde as giving us the direct causal effect, because इसमें अगर कोई correlates थे तो उनका effect भी capture हो रहा. So it was measuring this total change in y, whether it's due to x1 or x2, and assigning that to x1. In a multiple regression, the beta 1 hat measures in सारे variables को, क्योंकि मैंने as a control डाल दिया अपनी regression में. So when I estimate beta 1, that beta 1 is measuring not the x1 का full total effect on y, but x1 minus these variables का effect on x1. So taking away, so effectively beta 1 multiple regression का beta 1 hat takes away this indirect effect by regressing y on the residual rather than x1.
सर एक
So
बात पूछनी है.
sorry,
सर ये हम लोग सिंपली पार्शियल डिफरेंशिएशन से यही काम नहीं कर सकते क्या?
partial
अगर हम
differentiation
मल्टीपल लीनियर रिग्रेशन को हम पार्शियली डिफरेंशिएट कर दें बीटा 1 के थ्रू.
नहीं, वो partial differentiation helps us in understanding what does beta 1 mean, उसकी interpretation क्या है. This is talking about कि वो उसकी value estimate कैसे होगी, because beta 1 की value हमें given तो नहीं है ना, we still need to estimate its value. So I am saying if you apply OLS to estimate the value of beta 1, जो multiple regression में आपके पास value आएगी in general, generally speaking, it will be a different value from what you will get in a simple regression, because the formulas are different. So the multiple regression formula is more like regressing y on, not on x1, but on its residual, x1 net of the other variables influence. जो simple regression है, that is simply regressing y on x1 and it's assigning all the total change in y to x1, right? Multiple regression ये कह रही है कि in that total change in y, अगर x1 के कोई correlates भी हैं इधर, उनका effect भी add up हो रहा है. So let's try to clean our x1 variable. Let's remove the portions that are correlated with other variables and then measure sort of the change in y. So you can think of it like that. Anyway, so you will need to spend some time thinking about this. But this is looking at the formula this way gives us this partitioned regression interpretation, or a um, partial effect interpretation of the slope coefficient in a multiple regression. तो इसको पार्टीशन रिग्रेशन कहते हैं अगर आप रिग्रेशन को दो स्टेप्स में कर दें, पार्टीशन कर दें अपने एक्स वेरिएबल सेट को. ऑब्वियसली अभी तो हम x1 की बात कर रहे हैं beta 1 की. If we were interested in beta 2, we will need to in the first step regress x2 on x1, x3 all the way up to xk, all other x variables, obtain the residual which we would have called r2 hat, and then regress y on r2 hat. That slope coefficient would have been equal to beta 2 hat. So each slope coefficient in the multiple regression can be thought of as giving us the effect of that variable netted of its correlation with other x variables on y. Okay, we need to stop and do that quiz. Menahil, over to you.
Yes. Guys, the quiz is live. You have 5 minutes to attempt it. Good luck. So it's 11:08 right now. We'll resume our class at 11:13.
Okay. I hope all of you are back. Your quiz. All right. So we have talked about the simple and the multiple regression and the OLS slope estimator formula in each of the two models. And we've also talked about that the estimate you will get of the same slope, beta 1, the slope with respect to the x1 variable in each model, will generally not be equal. So when you, which means what? Which means that when you add additional variables to your regression, the slope on the existing variable will change in value, right? And you can see how it will change. So the formulas are different. So the way you will compute the slope in a multiple regression is different from how you will compute it in a simple regression, right? So this is true. If you read the book, it also gives you, okay, so here we are talking about a general multiple regression, but if you added just one more variable, so x1 and x2 are the two variables in your model, and let's say that was the true model, so nothing else in the error term was correlated with x1 and x2, and so that we got, you know, unbiased estimates of those. So if the true model had two variables only, then you can actually write an equation relating these two coefficients. So the beta 1 tilde, which you get from the simple regression, equals beta 1 hat from the multiple regression plus this term. So it's not equal to it, it's equal to beta 1 hat plus beta 2 hat times delta tilde, where delta tilde is a regression of x2 on x1 slope coefficient. So think of it like this. This one, the simple regression coefficient, gives us the total effect of x1 on y. In calculus notation, you can write it as dy by dx1, right? That total effect can be the sum of the direct effect, which is the partial derivative with respect to x1, plus an indirect effect, which is the change in y due to x2 changing, keeping x1 fixed, right? And dx2 by dx1. So how much, अगर x1 में change आए तो x2 में कितना change आएगा, that's given by this derivative dx2 by dx1. And x2 का में change आने से just that alone, how would that affect y, that's given by this partial derivative. So you will need to, you can write it as this thing, right? So the total effect is what the simple regression gives you. The multiple regression with both x1 and x2 gives you these direct effects. So the direct effect of x1 on y, the direct effect of x2 on y. And the multiple, wo jo simple regression ka coefficient hai, it's actually giving you the total effect, which is the sum of the direct and the indirect effect going through x2. Anyway, think more about this. So for now, let's bracket it off. Let me erase this. All right. So your book talks about this and also talks about what is the cost of omitting such confounding variables from your regression. So what is the cost of estimating a simple regression when you should have really estimated a regression with both x1 and x2? So if you don't include x2 in your regression, that is going to OLS estimates of beta 1 will give you biased estimates of the true effect, the direct effect, right? And what will be the magnitude of that bias? When would you have that bias? Obviously, when there is an indirect effect, that second term. Okay, so that you can read up on your own. What I wanted to talk about in the remaining time is look at the variance. So abhi humne baat ki ke if you add controls, additional x variables, that has an effect on the way OLS computes the slope coefficient, the existing slope coefficient. So inke formula is different hai. But does adding more, so point estimates will be different in the multiple regression compared to the simple regression. But will the variances also be different? So how will you calculate the variance when you have more than one x variable? in your regression. So yes, the variance formula will also change. So here's the variance formula that we derived previously for the simple regression. So SST, the denominator, so the numerator sigma square is just the variance of this error term in my regression. Denominator में आपके पास जो जिसको मैं SST बोल रहा हूँ, that is simply this thing. Actually, it's the total sum of squares in the x1 variable. So this is, I'm defining this as SSTX. SSTX हमने पहले कहा था, but now because we are calling it x1 to be consistent, so I'm just going to call it SST1. So that's the formula for the variance of the slope estimator in the simple regression model, right? What happens to that formula in the multiple regression? So beta hat, the other thing I've done is I've made this formula generic. So beta hat j instead of beta hat 1. So आपने किसी भी slope coefficient का, so j goes from, in this formula, j goes from 1 to k, right? As it does for over here. So this is the formula for the slope coefficient. Any slope coefficient in the model can be expressed as the corresponding residual multiplied by y divided by its residual per sum of square. ये जो variance of beta hat j है, again this is the variance of the slope coefficients in my model. It is different. This formula is different from that formula because it has this additional term in the denominator. 1 minus r squared j. So what is this r squared j term? Anyone, can you guess? ये r squared j क्या है?
So is it the goodness of fit?
जी. So r squared is a measure of goodness of fit of a regression model. So how do we calculate r squared of a regression model? It's the explained sum of squares over total sum of squares. Sum of squares of what? The dependent variable. So the total sum of squares is denominator में जो आ रहा है, that's yi minus y bar whole squared. और जो explained sum of squares है वो क्या चीज है?
Sir, y hat minus y bar.
The sum of squares in the y hat variable, the fitted value. So y hat minus उसका mean जो कि y bar के बराबर ही है, square. Right? And this r squared is a goodness of fit measure, and it varies. We can show that it varies between 0 and 1. It takes values in the 0-1 interval. And as the r square value goes up, it means that my model explains a lot of variation in my y variable. So my x variables taken together, if r square is 0.8, it means that my model, this linear model in the different x variables, explains 80% of the variation in my y variable. So बाकी जो error term है वो बाकी 20% variation को वो explain करके. Residual sum of squares is 0.2. The explained sum of squares as a fraction of the total sum of squares is 0.8. Right? So a higher r squared value is in some sense good because it means that your regression model is does have explanatory power. It explains the variation in the y variable. So your x variables explain more of the dependent variable. But this, however, is not r square of this model because it has this j subscript. जो कि beta hat j है ना, SST j, r square में भी j subscript है. So which regression model is this an r squared of? Anyone? This is the r squared of that extra regression that we were running, the auxiliary regression. So this is the r squared of the regression of xj, क्योंकि उसके beta hat j की बात होगी ना, xj के coefficient. So the regression of xj on all other x variables. right? So अगर बाकी सारे x variables xj के साथ बहुत correlated हैं, if they explain a lot of the variation in xj, then r square j will be close to 1, right? अगर तो वो perfectly predict कर देते हैं xj को, if xj is a exact linear function of the other variables in the model, then r square j equals 1. Then we say we have a perfect multicollinearity. So r squared j degree measures the degree of what we call multicollinearity in our model, or the degree of correlation among the x variables. So multicollinearity is a fancy term for correlation among x variables. So अगर r square j की value high है, so that means that my x variables are highly correlated with xj. So the degree of multicollinearity is high. And if r square j is low, then xj is not very correlated with the other x variables. So the degree of multicollinearity for that specific slope coefficient in estimating that is low. So is it good to have, now look at this variance formula. Is it good to have a small r squared j value or a large r squared j value? So before you answer that question, is it good to have a small variance on your beta hat estimates or large variance?
So small variance.
Small variance.
Yeah, small variance means that I have obtained a precise estimate of my slope coefficient. उसकी estimate की value different random samples में बहुत ज़्यादा vary नहीं करेगी from what I've got in this sample, right? So a smaller variance is always better. So r squared j की value बड़ी होगी तो variance small होगी, या उसकी value छोटी होगी तो variance small होगी?
So जब
So
छोटी
what
होगी तो
happens-
variance small होगी.
Right. So the variance of beta hat j, notice that r squared j is coming in the denominator. So लेकिन it is coming with a negative sign. So अगर कोई चीज denominator में आ रही है तो उसकी value बढ़ने से variance की value कम होनी चाहिए. But क्योंकि ये negative sign के साथ आ रहा है तो इसकी value बढ़ेगी, तो 1 minus r squared j की value कम होगी और इसकी value कम होने से variance की value बढ़ेगी. So if r squared j goes up, variance of beta hat j goes up, and that's not good, that's bad. So basically what's the upshot? The upshot is that adding other x variables which are highly correlated with x1 is going to increase the variance of my beta 1 estimate, right, due to this multicollinearity problem. अगर r squared j की value 1 हो जाए तो 1 minus 1 we have a divide by 0 problem. In fact, we will not be able to even obtain the beta hat j की value. We won't be able to estimate this regression. That's called a perfect multicollinearity problem. So r squared j is equal to 1 का मतलब है कि there's a very high, so that's like having a correlation of value 1, right? So a perfect multicollinearity means that there's an exact, I can write an equation, an algebraic equation without any error term. I can express one of these variables xj as a function of all the other x variables, and there will be no error term in that equation, right? So that's bad, because that means that one of my variables can be written as an exact function of the other variables. So I cannot estimate the model as is. I will need to drop that variable or one of the variables in my model to be able to estimate it. In fact, you will see in chapter 3 it is one of the assumptions that we need to be able to estimate this. And वो जो assumptions आपकी model की लिखी होती है ना, that you need in order to estimate that model and obtain, derive the mean and variance of beta hats. One of the assumptions is that there is no perfect multicollinearity among my x variable set. So no x variable is a linear function of the other x variables in exactly. Okay, I've run out of time. I wanted to talk about an example from the book, chapter 3. Those of you who have class obviously can drop off and join your other class. But those of you who can stick back, let's just quickly do that.
Okay, let me share screen and I hope you can see. So this is an example from the book. The book, as I'm sure all of you have now gotten your copy of it. So this is trying to estimate a regression where you have log wage is the dependent variable, and on among the explanatory variables you have education, which is how many years of schooling you have, experience, which is how many years have you been working, and tenure, which is how many years have you been working with the current employer where you are now working, right? So we wanted to run a regression which said, okay, there is some variation in the wage variable in our data set. Some people are earning a higher salary than others. Let's ask ourselves how much of that changes in log wage are due to education, labor market experience, how long have you been working with us, your seniority in an organization. So these are the three right-hand side variables. Anyone who would like to interpret? We had a sample of 526 individuals from the US labor market, and we estimated this regression. The results are reported in front of you. And so if I may go up a bit. I don't want you to read off the interpretation. What does the regression tell us? So we have a coefficient of a positive coefficient 0.092 on education, 0.0041 on experience, and 0.022 on tenure. And obviously there's an intercept term which is also positive 0.284. Anyone who would like to interpret this regression? Comment on the results we have got.
Yes, sir, it would mean that if we hold experience and tenure constant, then an increase in 1 unit of education would lead to 0.092%, 0.092 increase in the wage.
Right. So if I hold experience and tenure constant and then change education by 1 unit, so that language suggests that if I were to take a partial derivative of this equation with respect to education variable, keeping other variables, treating them as fixed constants. Just differentiate with respect to the education variable. Obviously, because education की कोई squared term या non-linear term नहीं आ रही, there's only one term, 0.092 education. So if you were to differentiate, you will be left with plus 0.092. So a 1 unit change in education, keeping those other two variables fixed, is associated with, not leads to, we don't like to use causal language when interpreting regression results. So we say कि a 1 unit increase in education, keeping experience and tenure fixed, those are the variables fixed, is associated with a 0.092 unit increase in what? In our dependent variable, which is log wage. Or we can say a 0.092 unit increase in predicted log wage hat, right? Because that's the dependent variable in this equation. So अब आपने 0.092 unit increase in wage उसको कहा. So I wouldn't call it wage because wage is not the dependent variable, it's log wage. But there is a connection between a variable which is in levels and a variable in logs. So by the way, one side remark is in econometrics, whenever we talk about taking a log of a variable, we always talk about taking the natural log, not log to the base 10, but log to the base e. So even though they've written log, and typically आपकी math की किताबों में log means log base 10, but here it means log base e. So really they should have written ln, but they just follow this convention. So log to the base e की property ये है कि अगर मैं इसको 0.092 को 100 से multiply कर दूं, तो that will give me the percentage change in the original variable in levels. So original variable मेरा wage था, उसका पे मैंने log लिया, natural log. So अगर मुझे चाहिए, मुझे अपना effect measure करना है wage में, not in log wage, because 0.092 unit increase in log wage, what does that mean, right? People might be confused if you explain your regression results like that. So you would want to talk about the effects or the partial effects, partial correlations, these coefficients in terms of the wage, original wage variable. So उसके लिए you will multiply 0.092 by 100, you will get 9.2. So 9.2% increase in wage. That's what I can say. So I can interpret it in two ways. I can interpret it either as I said initially, a 1 unit increase in education, keeping these two variables fixed, is associated with a 0.092 unit increase in predicted log wage. Yeah, 0.092 unit increase in log wage. That's one way. Or I can say it is a 1 unit increase in education is associated with, keeping those two fixed, is associated with a 9.2% increase in wage, right? So so that's how log variables are treated. We'll talk about that in more detail. But so for now, let's in a later class. So now for now, let's just interpret in terms of log wage. Anyone who wants to say something more than just interpreting the individual coefficients? What does this regression tell us about the different variables? Is that what we would have expected, or would you have expected a different regression results?
Sir, I have a question. So just to repeat what you said, that a 1 unit increase in education will lead to a 0.092 increase in log wage hat, or it could also be said as that 1 unit increase in education would lead to a 9.2% increase in wage. Is that right?
Except I wouldn't use the language lead to. I will say it is associated with.
Okay.
And keeping experience and tenure fixed. So if I take two people if I take a group of individuals with same experience and same tenure, कि उनकी labor market मतलब they've all been working for 10 years और इस company में वो 2 सालों से काम कर रहे हैं, और ये 2 groups of individuals हैं, एक की education जो है उन्होंने college complete किया हुआ है, दूसरे group ने नहीं किया हुआ, right? So उनकी education में 4 years का difference है. तो हमारी regression क्या बता रही है हमें? उनकी log wage में कितना difference होगा? Group A has 12 years of schooling, Group B has 16 years of schooling. Experience and tenure is the same for both groups. So what will be our predicted difference in the average log wage for the 2 groups? It will be 0.092 multiplied by 4, right? So we are not making any causal claims, but we are saying that in the data we have found a positive association. As your education increases, your log wage tends to go up by 0.092 units for every unit increase in education. So education 4 units से अगर increase करिए, अगर 4 साल ज़्यादा तालीम है आपकी, तो 4 times 0.092 increase हम expect करेंगे in your log wage, predicted log wage. ठीक है? तो so that's what we mean कि हम दूसरे variables को fix hold कर रहे हैं. So just focusing on education. So but that I think आप लोगों को तो that shouldn't come as a surprise, because we are used to, as economists, we are used to talking about, we have models which contain many variables like demand equations. So a quantity demanded responds to the price of the good, but it may also respond to the price of a complementary or substitute good. It may also respond to the income of that consumer. So हमारे पास 3-4 वेरिएबल्स हैं उस मॉडल में. अगर हम सिर्फ ओन प्राइस का इफेक्ट देखना चाह रहे हैं क्वांटिटी डिमांडेड पे, तो देन वी से कि ceteris paribus, keeping other variables fixed, what is the change in quantity demanded if the price goes up, right? So that's the same ceteris paribus thing that we are doing here. So we are saying keeping experience tenure fixed, keeping them constant. What is the change in my y variable if education changes? And that's given by the coefficient on education. ठीक है? Any other remarks on this regression? Would you have expected the coefficients to turn out the way they did? मतलब would you have expected कि सारे variables का positive effect ही होगा wage पे? या you expected कि किसी का negative भी हो सकता है, zero भी हो सकता है? Did you expect the coefficients, the relative magnitude of the coefficients to be the same कि education का coefficient magnitude wise सबसे बड़ा होगा, then tenure, then experience? Is that what you had expected?
In this case, I don't think we would think that any of the variables would have a negative effect on the log wage. But I think
why is that?
Because experience and tenure, like intuitively, you would think that they would, the more that you have of that would lead to, would be associated with a general increase in wage.
Right. So you would expect employers would value more experienced workers. They'll pay them a higher wage, and they'll pay a higher wage to workers who have been with the company for a longer period. So वो जो ज़्यादा senior staff है उसको ज़्यादा salary मिल रही होगी, compared to someone who has the same level of education and same overall labor market experience, but somebody who has been with the company for 10 years will probably get a higher wage than somebody who has only been there for 2 years or who has just joined, right? जिनके tenure की value 0 है. So you would expect so I think the most reassuring thing for you guys would be that education does have a positive coefficient. Employers do seem to value more educated workers, workers who have a higher level of education compared to people with lower level of education, keeping experience and tenure fixed, right? It may be that they value you. So if we take this regression literally, okay, this describes how employers set the wage for different workers and how they value these three different traits about a worker. What does it tell us? So if they are deciding how much wage to pay a fresh college graduate with 16 years of education compared to someone who's dropped out of school after doing intermediate but has been working since, so उसकी तालीम तो आपसे कम है, 12 years है, but उसका experience आपसे ज़्यादा है. He has worked 4 more years than, right? So he has more labor market experience than you have. So how will they trade off these two things? Would
the
the
law
fresh
wouldn't- Yeah,
college graduate get a higher salary than the intermediate pass with 4 years of experience working at that same company?
yes, we could say that because the education variable has the highest coefficient. And the surprising thing for me definitely was the fact that experience in the labor market didn't have a higher coefficient.
Yeah. So नहीं, but आपने मेरा question directly answer नहीं किया. You kind of dodged it. So मतलब you could calculate that, right? There's an individual A with 12 years of education, 4 years of experience and 4 years of tenure, क्योंकि वो चारों साल उसी कंपनी में काम कर रहे हैं, so tenure also equals 4. And there's an individual with 16 years of education, 0 years of experience and 0 years of tenure. So in a predicted wage according to our model, इन दोनों में से किसकी ज़्यादा high हो, मतलब who will get a higher wage of these two? That's a calculation that we can do, right? We can calculate the predicted log wage for each individual. एक की एजुकेशन 4 साल ज्यादा है, दूसरे का एक्सपीरियंस और टेन्योर 4 साल ज्यादा. So आप so you still want to stick with your answer के जिसकी एजुकेशन ज्यादा है उसको ज्यादा मिलेगी.
Just a second, sir. I'm calculating.
So experience और tenure दोनों के coefficients अगर आप add भी कर लें तो you get 0.0261, right? 0.0261 compared to 0.092. So that's like, you know, 1/3 भी नहीं है उसका education के coefficient, right? It's less than 1/3 of that. So एक case में experience और tenure का delta, the change is 4. दूसरे case में education का delta is 4. So obviously जिसकी education 4 साल ज़्यादा है, he will win out than the person who has more additional 4 years of experience at that. So, but yes, experience ka coefficient is the smallest. Actually, we will talk about later on in this course ke, it's not a fair comparison. So this horse race that we have between the different beta coefficients, we generally, if we want to know okay, which of my x variables is more important, has a bigger effect on y, instead of looking at beta coefficients directly, comparing the beta coefficients, because in beta coefficients का एक problem ये है कि they will change if I change the units of my x variables or y variable. And they are also obviously a 1 unit change in each of these variables does not mean the same thing, right? Given के sample में कितनी variation है. So वो जो labor market experience है, you have some workers, older workers who may have who may have been working for 40 years or 30 plus years, right? Who have lots of experience. And you have some people with 0 years of experience. So usme us variable may range of values that it takes is larger. So maybe a 1 unit change is small when you compare the range of values that it takes compared to an education type variable जिसमें हो सकता है 10 साल तो सारों की minimum because we have data from the US, so वहाँ पे compulsory schooling है 10 साल education तो हम expect करेंगे सारे workers की होगी, फिर कुछ की 12 साल होगी, कुछ की 16 होगी, 14 वाले भी कुछ होंगे, right? But so it takes values between 10 to 16 की range, right? So उसके अंदर एक साल का a 1 unit increase might mean, you know, in relative terms, might mean a larger change than a 1 unit increase in an experience variable which ranges from 0 to 60 in value. So because the different variables के, you know, units, range फर्क है, the range of values that they take. So 1 unit change in each variable may not signify the same amount of change, right? So इसलिए जो beta coefficients हैं वो तो 1 unit change का आपको effect बता रहे हैं ना on y का association with y. So इसलिए we can do something better. We can normalize all the x variables and then run the regression, and then we will be able to compare the slope coefficients to see which variable has the biggest effect on y. But this is, you know, this is still good enough for the purposes that the kind of questions that we were asking. Okay, if you compare want to compare two specific kinds of individuals, sure, आपकी regression जो है उनकी predicted wage का difference बता देगी, predicted log wage. Okay, so we are almost to the end of the office hours. Any questions? Stop sharing.
Yes, sir, I have a question.